A few years ago, a sixth former informed me that The Discriminant sounded like the perfect action movie. I'm inclined to agree, but the truth is even more exciting. So yeah, we're going to have a look at the discriminant. But before we can do that, we need to look at the quadratic formula. There it is. We've obviously used the quadratic formula many times to solve quadratics, and I'd like to do these three quadratics as an example. So obviously we say that we have got A and B and C. And we substitute those values in. So we've got minus 3 plus or minus the square root of 9 minus 4 times 2 times 1 all over 2. So that would give you minus 3 plus or minus the square root of 1 over 2, and that gives you two possible solutions. It gives you one with the plus and one with the minus. If we use the plus, that's minus 3 plus 1 over 2, that is overall minus 1. And if you use the minus, that's minus 4 over 2, that's minus 2. So two different solutions there. What about for the second equation? Well, A is 1, B is minus 10 this time, and C is 25. So we're doing 10 plus or minus the square root of 100 minus 4 times 1 times 25, all over 2. Simplifying that, we get 10 plus or minus the square root of 0 over 2. So we only get one solution, 5. What about this last one? A is 1, B is 6, and C is 10. So if we sub all this, we get minus 6 plus or minus the square root of 36 minus 4 times 1 times 10, all over 2, which goes to minus 6 plus or minus the square root of minus 4 over 2. We run into a pickle if we type that into our calculator. For the further mathematicians at the back of the audience, I'll invite you to just shut up a sec. That doesn't have any solutions. So with the quadratic formula, we kind of had three scenarios here. We had two solutions, one solution, and 0 solutions. And we need to think about what actually made that happen was what was inside the square root. So here we had a nice positive number inside the square root. That meant we could add the square root of 1, or we could take away the square root of 1, and those would give us different things. So if that number is positive, then we should get two different results. And the second example, we had 0 inside the square root. That meant it didn't matter whether we added or subtracted it, we only got one solution. So if it's a 0 number inside the square root, then we only get one solution. And on the third one, we had a minus number inside our square root, and we can't square root that. So we get no solutions. So if the number inside the square root is negative, there are 0 solutions. And that's basically what the discriminant is. It's the thing inside the square root. It's the b squared minus 4ac. So just to state this a bit more formally then, the bit inside the square root is b squared minus 4ac is the discriminant. Worth pointing out that the discriminant is not that. It is not the square root of that. It is the actual b squared minus 4ac itself. Now, what we said there is if that's a positive number, we get two solutions because we can plus and minus them. If it's equal to 0, then there's one solution. And if it's less than 0, there are no solutions because we're trying to square root a negative. I wanted to point out there were other ways of saying this. So another way of saying two solutions is distinct real roots. Another way of saying one solution is one repeated roots, and so on. And what sort of graphs would these actually represent? Well, if we're saying there's two solutions, then we mean one of two things. Well, we mean our quadratic obviously crosses the line twice, so it could be like that, or it could be like that. Whereas if there is only one solution, what does that mean about our quadratic? Remember, solutions are basically where we cross the x-axis. So that could mean that we have something like this that just touches the x-axis or something like that. We could have positive or negative quadratic. Whereas if there is a negative discriminant and we have no solutions, what does that mean? It means we don't cross the x-axis at all. Could look like that, could look like that. So make sure that you've got an idea, not just like greater than 0 equals 0, less than 0, how many roots there is, but why? It's because the graphs obviously will cross the x-axis a different amount of times. Now apart from that, there's not really anything to add for the discriminant, the rest is algebra. So let's do some of that. For our first question here, we want to find the value of k where this has equal roots. Now equal roots means that b squared minus 4ac, so there's one repeated root, is equal to 0. I would really encourage you to write something like that down at the start of every question that you think might be a discriminant question, because there are marks available just for that. Not if you do nothing with it, that's fine. Now in this question, A is 1, B is K, and C is 9. So if we sub them in, our B squared minus 4AC is equal to K squared minus 36. And we know that's equal to 0. We want this to have equal roots. So, well, just take the K across, I guess, or we could factorize it into K plus 6, K minus 6. But I prefer this, and we'll square root it, and we'll get that K could be plus 6, or it could be minus 6. Two options for what K could be. What about the second one? Find the range of values of K for which this has two distinct real roots. So, two distinct real roots, that's B squared minus 4AC is greater than 0. Two roots greater than 0. So let's work it out then. We've got A is equal to 1, B is equal to 4, and C is equal to K in this case. So B squared minus 4AC is equal to 16 is our B squared, minus 4 times 1 times K, so minus 4K is greater than 0. How would you solve that? Well, it's an inequality, so we do have to keep the sign. I think it makes most sense to me to just add the 4K to the other side and get K is essentially less than 4 as our answer. If you were tempted to do something like take away the 16, and we could have got to minus 4K is greater than minus 16, if you divide by a negative with an inequality, it flips the sign, so you would have got the same answer, just a different way around. Just worth pointing out. But anyway, K is less than 4. That's our range of values. Now here's a bit of a spookier question. We want to show the roots for this equation are always real. So it's not saying how many there are. We don't know what the discriminant is. But if it's talking about the roots always being real, then clearly we need to look at the discriminant. So in this case, we've got A is equal to 4, and B is equal to A, and C is equal to, oh, hang on a second. This isn't properly in quadratic form yet. If we want it to be a quadratic, we need one side equals 0, and one side does not equal 0, one side equals 4. So we need to subtract that 4. And our value of C is actually this A minus 4 thing. So now we can do the question. Now we can say B squared minus 4AC is equal to, well, B squared is A squared. Bit weird to have A in here as well. Minus 4AC, so minus 4 times A minus 4. Okay, well, let's expand that out, I guess. We will get A squared minus 16 lots of A minus 4, which will go to A squared minus 16A plus 64. Okay, so we're trying to show that this is always real. So what would that mean? Well, it means we need to show this is always positive, because then they'll have real roots. But how do we show this is positive? Well, we can factorize it. We can use a quadratic within a quadratic. And this actually will go to, times is to 64, adds to minus 16. It will go to A minus 8, A minus 8. In other words, A minus 8 all squared. And what do we know about square numbers? We know that they are always at least 0. They're always positive. So what we've got there is that B squared minus 4AC, our discriminant, is greater than or equal to 0. And that would mean that there are 1 or 2 roots. Because if it was equal to 0, it'd be 1 root. Then, there could be 2. And so in either of those scenarios, that is real roots that we've got there. So 1 or 2, real roots. And yeah, that's the proof. Good question, that one. Okay, let's finish off by looking at some exam questions. We've got here a quadratic equation has real and distinct roots. What does that mean? That means B squared minus 4AC is greater than 0. Greater than because it's distinct roots. Find the possible values of K. So again, we're going to say A is 3, B is 4, and C is 2K minus 1. Yeah, that's fine because it's an equal 0. Sub that all in, we'll get that B squared minus 4AC is equal to B squared is 16, A is 3, and C is 2K minus 1. That'll give us 16 minus 12, lots of 2K minus 1. And just be careful here, we're doing 12 times 2K. and minus 12 times minus 1, that will be a plus 12 at the end there. So overall, that would give us 28 minus 24k. But we know the discriminant is greater than 0 from what we said before. So we've now got an inequality to solve. I would probably move the 24k across and then divide by 24, I guess. So 28 over 24 is greater than k. You could simplify that to, well, 7 over 6, I guess. And we could put the k in front if we want. There we go. Okay, what about the second question? Find the values of k for which this has equal roots. Now, equal roots, that means just one root. That means that b squared minus 4ac is equal to 0 this time. So in this case, we've got a is equal to 2k minus 3. No rearranging needed, but it is going to have some factor expanding to do. B is minus k, and c is k minus 1. So let's put that into our b squared minus 4ac. Well, b squared, that's going to be minus k squared, minus 4, 2k minus 3, k minus 1. Okay, so this is basically testing our ability to expand things. What can you do with this? Well, we could make this k squared, that's not a problem. We could expand our quadratic, that's going to go to 2k squared minus 3k minus 2k, that's overall minus 5k plus 3. And then we could expand that again, so remember we're times it by minus 4, so minus 8k squared plus 20k minus 12. And overall that gives us what? Minus 7k squared plus 20k minus 12. And if you want that to have equal roots, that has to be equal to 0. Now, I don't like the look of that quadratic, so I'm going to change all of the signs, essentially multiplying both sides by minus 1. And then I'm going to try and factorize it. You could use the quadratic formula if you wanted, but I don't think I want to. So what could we get that would times up to 12 and get us up to 20? Well, we know they're both going to have to be minus numbers because they multiply to 12 and add to a negative. I think it's going to be 6 and 2, because that will give us 6k and minus 14k. Yeah, that'll work out. So our two valid answers then would be k equals 6/7 from the first bracket and k equals 2. Those are our two values where that has equal roots. Okay, let's bring the graphs back into it. So we've got a curve with an equation, x squared minus 6x plus k, that has two distinct positive roots. So we want to sketch this. Now, what do we know? For sketch, we need to know shape. Shape is easy enough. We want to know y-axis, and it goes to the y-axis at k because that's when x equals 0. And we want to know x-axis. Now, x-axis is going to be the solution to this, and we can't really do anything unless we know what k is. We just know it goes through there twice. So we're just going to have to mark k. I mean, do we even know k is positive? No, we don't. So it's just going to have to be a quadratic, I guess, that goes to the y-axis at k and hits the x-axis at 2 points. I think that's all we can do. Want to find the range of possible values for k and fully justify our answer. So for the second part, obviously if we've got two distinct positive roots, then that means that b squared minus 4ac is greater than 0. You'll notice that comes up a lot. So let's sub it in. So we know that a is equal to 1, b is equal to minus 6, and c is equal to k. If we sub that in there, we'll get minus 6 squared minus 4 times 1 times k is greater than 0. That would give us 36 minus 4k is greater than 0. And then we can add the 4k across, and we can say that k is less than 9. So yeah, our sketch was one possible value. It could have been higher up as well. Yeah, that's it, 6 marks. And then for a final question, let's bring completing the squared back in as well. So here, we've got to first put this in the form completing the square. We want to find p and q in terms of integers. So remember, what we need to do is obviously take out a factor of 2. We've also got our plus 53. Then we can, let's go over here, we can complete the square with what's inside the bracket. that'll be x minus 5 squared minus 25 plus 53, and we can expand that to lots of x minus 5 all squared minus 50 plus 53, so overall plus 3. Now, use your result to explain why this has no real roots. So it's not asking you to use the discriminant here, it's asking you to think about the sketch. And what we've got here is a quadratic, obviously, with a turning point of 5, 3, based on that. So if we go down to 5 across to 3, then our positive quadratic would look something like that. So how would we explain this? Turning point maybe is above axis. And we'd have to say it's a positive quadratic. And putting those two facts together, we can say it doesn't cross the x-axis. Okay, then on to B. The quadratic equation has real roots. So what does that mean? That means that b squared minus 4ac is greater than or equal to 0. It doesn't specify if there's one or two of them. And we want to show that this quadratic exists. So in this case, we'd say a is 2k minus 1. We'd say b is k plus 1. We'd say c is k. They very helpfully sort of group them together for us. And so we just find the discriminant. B squared minus 4 a c. Okay, expand. So we've got k squared plus 2k plus 1 minus, I guess, 4k, lots of 2k minus 1. Let's move that k over. So we've got k squared plus 2k plus 1 minus 8k squared plus 4k. And so overall, minus 7k squared plus 6k plus 1. And we know it's got real roots, so we know this is greater than or equal to 0. Now we want to change the signs. And we'll do this by times in both sides by minus 1. And that will change the direction of the inequality sign as well. So we have proven the statement that they want us to prove. Cool.